Okay, so today what we're going to do is kind of like a review of, well, it's not exactly a review, but we've done this before in this class, which is basically approximating areas under the curve, which that's what approximate integration is anyway. And what we used were rectangles, if you recall when we first started the whole idea of finding the area under the curve. And then we'd use sample points as left end points, right end points, or midpoints. And then depending on what we chose, sometimes we'd get an overestimate, other times we'd get an underestimate. And then at times, specifically for the midpoint rule, we'd get an overestimate on one part and an underestimate on the other part. And so we realized of all the methods that we use to approximate areas under the curves, with rectangles, midpoints was the way to go. Now, we're also going to learn to use the trapezoidal rule. So today, what we're going to learn is inserting trapezoids under the curve and using trapezoids to approximate the area under the curve. And you'll see that this one, along with the midpoint rule, are probably the two best rules to use to come up with a pretty accurate approximation. So basically, what we're going to need to do is we're going to need to use, so we will be using areas of trapezoids to approximate area under curves. So if we do a quick review of geometry, in geometry we learned that for a trapezoid, if we were to draw a trapezoid, we know that the bases are always parallel, and then this is the height. So if we have B1 and B2 in the height, then we know that the area of a trapezoid is 1/2 times B1 plus B2 times the height. And so that's basically what we're going to be using to approximate the area under the curve here. However, now one other thing I want to point out is if we have trapezoids standing up, that doesn't change anything because remember, the two parallel sides are always considered the bases. So this would still be base 2, base 1, and this would still be considered the height. So the area of this trapezoid or that trapezoid, they're found the same way. So although it looks like this is its base, by definition, the bases of a trapezoid are the two parallel sides. So when I'm finding the area of this, I would have to treat those as the sides, and then this would be the height. Okay, so let's start off with just an example. We'll do one example, and then that example should basically be good enough for you to pretty much do the homework. So what we're going to do is we're going to say approximate the area under the curve of y equals x squared from 0 to 1 with n equals to 4 using the trapezoidal rule. So let's actually do this. And so real quick, here's how this is going to look like. And so we know that the graph from 0 to 1 of x squared looks like this. And so what's the first thing we're going to do? We're going to have to divide this into 4 parts. And so delta x is 1 minus 0 over 4, which is 1/4. So if I divide this up into 4 equal subintervals, that would be 1/4, 1/2, 3/4. And so what we're doing is, see, we insert this, and how our trapezoids are going to look are like this guy. They're going to be kind of standing up, and the height's going to be on the base. So what we get is the first trapezoid, and then we have the second trapezoid, and then we have the third trapezoid, and finally we have the fourth trapezoid. And so what you notice is when I draw my trapezoids, I mean, it looks like it's covering the parabola perfectly, but if you notice, it slightly misses it. But you could see why the trapezoidal rule is so advantageous because of the fact that these trapezoids, they do a pretty good job of covering the curve. So Now, as always, we're going to find the area of each trapezoid. So we're going to say the area of the first trapezoid is going to be what? It'll be, so we can call A1 equal to um, 1/2 times base 1, which base 1 has a height of 0, plus base 2, which has a height of, and notice how to find this height, I have to plug in 1/4 into the equation. So it'll be 1/4 squared times the height, which the height is 1/4. Plus, then we'll say, okay, the second, or A2, which would be 1/2 times the height, or the base, which would be using the equation of the curve, so 1/4 squared, plus the second base, which would be 1/2 squared, times the height, which is 1/4. And then area 3 becomes 1/2 times 1/2 squared, which is this base, and then plus the other base, which would be 3/4 squared. Hopefully you guys see why I'm getting 3/4 squared, because this base would be, starts from the x-axis and ends on the curve, so I'm just plugging 3/4 into the equation, times the height, which, what's nice is, since these are equally divided, all of the heights are 1/4. So you could see that we're going to come up with a formula in a minute, and we'll generalize this, and then this would be what? 1/2 times 3/4 squared plus 1 squared times 1/4. So if I add these up, technically speaking, what do I notice? Every single one of these has a 1/2, and every single one of them has a 1/4. So by adding these, let's kind of simplify in a quicker way. We could say, look, they all have a 1/8. So let me factor out the 1/8 and then combine what's inside. So 1/4 squared is 1/16, plus that 1/4 squared is another 1/16, plus 1/2 squared and a 1/2 squared. I have two more 1/4, and then 3/4 squared plus 3/4 squared is 9/16, and then of course the last one is a 1. So if you notice, if I were just to get a common denominator, this would be what? 4/16, 4/16, that would be 16/16, and so I could combine them. So this becomes what? 1, 2, 6, 10, 19, 28, plus 16 is what? 44. 44/16. And now I could simplify these, which, what do I know? This simplifies with that. That becomes 22, and that becomes 4, and I could cancel it out one more time, which that becomes 2, that becomes 11. So what do I get? 11/32, which is my approximation. Okay, now, with that said, let's kind of generalize the trapezoidal rule. If you notice, so if we were to summarize this, let's just kind of generalize it and see what happens. Or it could be from A to B, it doesn't matter. So if we divide this up n times, what do you notice? The first trapezoid, second trapezoid, third trapezoid, fourth trapezoid, and so on. What you notice is every trapezoid, every consecutive trapezoid, they share a base. So what we notice is that the only trapezoids that don't really share a base is the first one, where no one shares this one, and then the last one, which this last trapezoid, see, this base isn't shared with anyone, but this base is shared with that, and then this base is shared with that and that. So basically, we could say approximate integral using trapezoidal rule. So we could say the area under the curve of f of x from A to B can be approximated by the trapezoidal rule as the following. So we would say the integral from A to B of f of x dx is approximately equal to what? It would be 1/2 times base 1, which would be f of x sub 0, plus f of x sub 1. And see, these are basically our partitions, right? Because that would be x sub 0, that would be x sub 1, x sub 2, and all the way to x sub n, okay? Times delta x plus 1/2. Then the next trapezoid, remember, it'll share f of x sub 1. It'll be f of x sub 1 plus f of x sub 2 times delta x, which, if we're assuming that we're dividing this up evenly, all of the heights would be the delta x. So remember, this is base 1, base 2, height. And the 1/2 is there because of the formula. Plus 1/2 f of x sub 2 plus f of x sub 3 delta x. And I'm going to keep doing this until I get to what? Plus 1/2 f of x sub n minus 1 plus f of x sub n delta x. So let's simplify this a little bit. So here's what we know. We know that all of these have a 1/2 in common, and all of them have a delta x. So what we could say is this is equivalent to what? Let's factor out a 1/2 and a delta x, or you could say delta x over 2, it doesn't matter. And what are we left with inside? It'll just be f of x sub 0 plus f of x sub 1 plus f of x sub 1 plus f of x sub 2 plus f of x sub 2 plus f of x sub 3 plus, we're going to go all the way until we hit what? F of x sub n minus 1 plus f of x sub n. Okay, now here's what we notice. See, other than the first side or first base, which if I come back to this picture, that base, which is 0, depending on where the function is, and the last base, every other base is being shared twice or is being counted twice, which you notice how I get f of x sub 1 plus f of x sub 1, which becomes 2f of x sub 1. Then I get f of x sub 2 and f of x sub 2, and I get 2f of x sub 3. And guess what? The last one where all a side will be used is f of x sub n minus 1. So what we notice is that this becomes what? Delta x over 2 times f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 plus 2f of x sub 3. And we're going to keep going. And the last time I'll have a 2 would be the f of x sub n minus 1 plus f of x sub n. And see, this is basically the formula for finding the area of the first n, or the n number of trapezoids, which, if you remember, we did this in example 1, and that the only example that we did. But this is basically the sum of the first n trapezoids. So that's basically what we use. And let's also say with delta x equal to b minus a over n, just so we know that we're dividing it up evenly. If we were not to divide this up evenly, then I wouldn't be able to factor out the delta x because it would change. But remember, we always like to divide it up evenly unless they tell us that, hey, these are the subintervals and they've broken it up, which we could still use the rule, this trapezoidal rule, except the delta x, I wouldn't be able to, it would change from this to that. But as long as delta x is the same, this is the sum of the first n trapezoids. Okay, so just to kind of come back to this first example, if you notice, what do? This first trapezoid, which is in fact a triangle, which that zeroes out and we get the triangle anyway, but that's what we have. We have 0 and 1/4 that we use to find the bases. And then look at the next one. We used 1/4 to find the first base, which is the same thing as that, plus 1/2, which that's the second base of the second trapezoid. And then look at the third trapezoid. It has the same side, the same base as that guy did, but it also has 3/4. And then the last trapezoid had the same base as the one prior to it, and then the last side, which notice, so the only side that's not shared is the first one and the last one. Other than that, everything else we're performing twice, hence that's where these 2's come from. Okay, so that basically wraps it up. We have the trapezoidal rule. So when you work on problems, you'll be asked to still approximate areas under curves using rectangles, whether it's left endpoints, midpoints, right endpoints, they'll let you know. And they'll also say use the trapezoidal rule. Okay, so that takes care of this section. If you have any questions, feel free to ask me.